Thank you for joining us here at I/O today. Hello to everyone on the live stream as well. My name is Rob. I'm an engineering lead on the Android Things team, and I'm joined today by Shikha, who is a product manager on our team. This is a Lenovo Smart Display built using Android Things. You can think of it as a visual Google Assistant or like a smart speaker with a display. You probably heard in the keynote already, or maybe in Vince's talk earlier today, that these devices and others from JBL and LG will be available on store shelves starting this July, just a couple of months from now. Today, we're going to tell you the story of how we built these devices from prototype up to the production devices that will be available in a few months. Before joining the Android Things team, I spent most of my career writing software that ran on other people's devices, probably like many of you. But building a new piece of hardware at scale is different from the kind of work I had done before, and it came with a lot of new challenges. And today we're going to tell you about some of them. Our hope is that you leave this talk with a better idea of what it's like to build consumer hardware at scale and how Android Things makes it easier than it's ever been. It's not that scary once you know what to expect, so I hope that our story of prototype to production can help you build a device of your own.
If you are a software developer thinking about building consumer devices, here are a few things you probably care about. First, you want to build your product features without having to worry about the underlying platform. You also want to be able to swap out underlying hardware seamlessly without affecting your application layer as the technology or product needs evolve over time. You obviously want your devices to be secure. I think it's obvious why security is increasingly an essential requirement for smart devices. They hold the keys to our homes and our personal information. What's probably less obvious is why it's hard to provide this kind of security. It's incredibly expensive to harden products out of the gate and to keep them updated over time. Meanwhile, there's immense cost pressure from end customers, and it's hard to amortize costs without large volume. We know this at Google, since we've been doing this for many products. Coming back to you, finally, if you're building a consumer device, you'd want to manage release and update channels over time. Android Things was designed with all of these needs in mind. We provide turnkey hardware in the form of pre-certified system-on modules, or what we call as SOMs. The SOM includes the CPU, Wi-Fi, Bluetooth, memory, and other critical hardware components. Think of this as a small computing platform that you can use to build a variety of IoT devices. We bring up the operating system on new SOMs, test it, and certify its suitability for production devices so that you don't have to do any of this. Later on in the talk, we'll give you an inside look into some of this work that Google handles for you. You provide the application code and wire up the peripherals, and Google takes care of the rest. What you see here are smart displays from Lenovo, LG, and JBL. As Rob mentioned, they are built using Android Things. In fact, if you look under the hood, all three products have the same SOM, which is pretty cool. These devices have far-field microphones that can hear you from the other side of the room, and built-in speakers that can answer back across the room, just like a smart speaker. But now, we also have a touch screen, which makes it possible to see visual results. This is quite cool if the result happens to be a list of restaurant nearbys or a map showing you your commute conditions. We announced this earlier this year at CES, and we're very proud of the reception we received. Let's dive a little deeper and see how we built these. About a year back, we at Google were wondering if we could build a visual Google Assistant. This would enable deep integration with other Google services such as YouTube, Photos, Maps, and so on. Building a consumer device, though, is typically a long process. But for a fast-evolving space like smart home devices, time to market is extremely important. We wanted quick turnaround time, and this is exactly where Android Things shines. Our goal is to make it possible for software developers like you to build consumer devices at scale. But that's a hard thing to get right in a vacuum. It takes real-world experience in building and shipping a lot of devices to know that you've really done it. This project would give us the perfect opportunity to do that. In this case, our customers were software developers from other internal teams at Google, such as the Google Assistant team. For smart displays, while they took the lead on building application software, we iterated on the platform. As a result, we were able to get these from prototype to production super fast, and we now have a stronger platform for you to build on. We started by building some proof of concept hardware for smart displays. Our goal was to learn from that and to use the device to kick off broader discussions across the company. So we took a few weeks and some spare parts and built this.
This is our first proof of concept hardware. This is running on some hardware that we had used previously to deliver an Android Things powered smart speaker. I built this case with my son. It cost me about 2 Pokemon cards. He still wonders when he's going to get his bricks back, though. This device doesn't have all of the hardware that ships on the final devices. For example, it's missing a camera. It doesn't have the volume up, down buttons or mute of any sort. But that wasn't the point of this device. For this one, what we were trying to do is show just the basics of what we thought we could achieve with the smart display product to get some conversation started. The mic on this one in particular was kind of tricky to use. It wasn't meant for this kind of use case. You needed a quiet room, and you had to stand in just the right sweet spot. But with a little bit of practice, it was possible to pull off a pretty convincing demo with it. On top of the Android Things platform and the smart speaker code that we already had, we built a small Android application to drive the display and show off some of the key use cases we thought were going to be important for this kind of device. One of the first things we did with the display is to transcribe your query as you spoke it. It was a basic proof that the whole speech recognition pipeline was up and running properly, and it looked pretty cool in a demo. Next up, we added some support for a rudimentary, what we call a knowledge card, that'll show a brief snippet of text and a photo along with answers to certain questions. This device couldn't play video yet because it didn't have the hardware required for that, but it could stream music already, just like a smart speaker. So we added title track display and media transport controls like pause and skip. And then finally, we took a rough cut at the ambient screen, which is what the device does when it's not doing anything else. It showed a photo slideshow and a weather forecast. So like I said, just kind of a basic set of functionality that we could use to show people what we thought we could build out of this. It only took about 2 weeks and a small team of people to get this working. But the result was actually surprisingly close to the architecture of the final products that are shipping in a few months. The changes between what we built here and what we're shipping are basically incremental changes. Fundamentally, what we built and what we're shipping involves the smart display application at the top of the stack, running on top of Android Things on top of a certified, what we call a SOM. Android Things brings the hardware support, the security, the application framework, and the update mechanism, while the smart display application brings all of the Google Assistant integration and the visuals for the device. Don't get me wrong, there was definitely a lot of work to do between here and what we're shipping this summer. But as I said, the fundamental architecture is the same, and it was a matter of incrementally building out the feature set from here. We practiced the demo routine with this device and set up meetings across Google over the next few weeks. People got a kick out of the brick case that we built, and we had a lot of great discussions and some debate about product features we should support, about Android Things, and about what we should do next. Overall, the demos went really well, and we got the buy-in that we needed from key stakeholders across Google to move on to the next step with this project.
Now that this was going to be real, we kicked off a few steps in parallel to scale up our efforts. First, our business development team started discussions with potential OEM partners. In this case, an OEM, or an original equipment manufacturer, refers to a company that will build and sell the device. They come up with the industrial design and the physical look and feel of the product. They also pick parts like the display, camera, microphone, and other audio out components. If you were to build a device on Android Things, you will be the one responsible for case design and component selection. In place of this step, you might find an industrial design firm to work with or a factory to build your product. A lot of details here were handled by our OEM partners, and we are not going to cover them today. In parallel, we started finalizing the hardware requirements for the product. The proof of concept device used a SOM that we had used to build smart speakers. But you can build anything else from it that has similar requirements as well. For smart displays, though, we needed something more powerful to support use cases such as video playback. Fortunately, we had some SOM options in our roadmap that we started evaluating. Finally, in parallel to the OEM selection and SOM selection, we got started on the application software. Google had already built out the Assistant backend and client software for smart speakers, but turning a smart speaker into a smart display isn't just a matter of plugging in a touch panel. There's a lot of new work around the home screen, the video playback experience, the maps and photos integration, and essentially all the other visual features that we were trying to build with this. Turning the application software from a humble proof of concept device into a production device was going to take a lot of time. Most of the software work was responsibility of developers outside our team, and they needed to get started right away. These engineers, who are software developers like many of you, don't want to have to think about the underlying platform or the hardware. But because we are building this on Android things, they don't need to. Like we mentioned earlier, we can decouple the two. The application engineers work on top of the Android framework, just like any Android developer would. Their application can run on any hardware with Android Things support.
So at this point in the project, it's July of last year. We're about a month and a half into the work. We've got our proof of concept hardware. We've got some business development work underway. We've got the hardware selection underway. And we're nearly ready to get started on the application software development in earnest. But in order to really kickstart development, we need to get some actual hardware into the hands of engineers and product managers and other folks at Google who are going to actually build this out. But as we said before, the hardware that we used in that proof of concept device was just a little too slow to use for more than just a demo. So we looked through the SOMs that we had in our pipeline and found one that met the requirements for this category of devices. And it happened to also be very easy to buy in quantity over the internet. And we had Android things already kind of running pretty well on it. So we decided to use this as the basis for some provisional hardware that we would build to unblock the application engineers so that they could get started on their job while we finished out the hardware bring up. We knew that we would swap this hardware out later when it got closer to production, but that didn't worry us because, as we've said, we're building on Android things, and that gives you the isolation from the hardware that you need to be able to do that. The second problem we had, though, with the provisional hardware was that it was a development board kit, similar to the IMX7 kits that we're giving out here at I/O, which means that it had a display and a camera connected to the baseboard through flat flex ribbon cables. You can obviously work like this, but it's a little difficult to manage if you have more than one on your desk, for example. And we wanted to give these out to a lot of Googlers. For the first few weeks, we literally held the thing together at our desks with cardboard and rubber bands. But that wasn't going to scale to the quantity that we wanted to deliver. For that, we needed a more solid enclosure to keep everything in one spot. And by the way, if you do complete the scavenger hunt here at I/O and you get an IMX7 kit, make sure to keep the packaging. It turns into a handy stand, so you don't have to build one yourself. So this is the enclosure we came up with for our first provisional hardware. Honestly, Android things didn't really help or hurt either way in the building of this case. But I had a lot of fun making it, and I learned a lot in the process. So I hope you don't mind if I geek out for a few minutes and tell you a little bit more about this design and how we built it. It looks pretty plain from the front. The point is that it's just enough to keep the hardware together and give you a rough sense of the form factor that we had in mind. There is a camera module at the top, some microphones that we had manufactured locally here in Mountain View in the middle of the top, and of course the big touch screen in the front. Here's a quick view of the back. The SOM and the carrier board are mounted in the back of this big piece of wood that I call the bezel here. Just like most of the rest of the hardware, you can get to most of the ports easily from the top. And there's a little access for the reset button on the side, which is very important when prototyping. I want to point out here, though, that pretty much none of these components match the final hardware. Obviously, as we've said, the SOM is different, so is the camera, so are the mics, so is the display. But again, not an issue because we're building Android apps on this, and they don't really care so much about the specific hardware underneath. Building this prototype was my favorite part of the project because at the time the deadlines were far enough away so that they don't make that crushing sound they do when they get a little closer. And we were still a small team that needed to be scrappy and pretty resourceful. So I literally built this case in my garage over a few weeks. And the best part of that is that I got to buy a new tool. Not just any tool, but a 60-watt laser cutter, which of course I got off the internet. I literally learned how to use a laser cutter for this project. I iterated on the design in my garage over the course of a few weekends. It was my first time using any kind of 3D modeling package to do this kind of design. My first time ever using a laser cutter. And I basically learned by watching videos online. And the point here is that if this is the kind of thing you like, yes, you can do it too, and you'll probably have a lot of fun doing it. The material that I tried first was this birch plywood. It's about 3 millimeters thick. You can get it in quantity from the net very easily, 2-day shipping in stacks of 25 or 60. If you go for the bigger, if you go for the batch of 60, it's maybe $1.50 a sheet or less, so it's pretty cost effective. When I first tried building this out, I wasn't very efficient with my material use. It would take maybe 2 or 3 sheets of plywood to build enough parts for a case. But eventually you want to get a little more optimized, waste a little less material. And as you see here, I managed to fit the whole case into a single 12-inch square sheet of plywood. I did have to fit one of the sides inside of the bezel to make that work. It was a lot of fun it was a big challenge to figure out how to get this all into one sheet of plywood. A lot of fun to overcome that. But laser cutters only cut in 2D, which meant it's a little hard to work a fastener like a screw into the design. So this one is all friction fit. I came up with a tab and slot design where you could put it together by hand and it would stay together pretty securely. And the best part of that was that it was actually real easy to service in the field. If a connector comes loose or you need to change a jumper, you can snap the thing apart with your hands. You don't need to find a screwdriver. You fix it, you put it back together, and you're good to go. We tried a few variations in other materials, such as the acrylic you see here. I think it looks much better than the wood. Obviously, this semi-transparent red is really cool. But what we found is that in acrylic, the thickness, for us at least, the material we had, the thickness varied too much across color and even within color, so that when we put some of the cases together, they'd just fall apart on a desk, or they'd fit together so tightly that the acrylic would snap at the weak points, which turned out to be the 90-degree cuts in the material. So we decided to go with the wood after all, because it was going to be more robust for us. I cut about a dozen, enough parts to make about a dozen of these cases. We brought them into the office, had some people assemble them so that we could try out the design. We iterated on it a bit, eventually settled on a final design and sent it off to an internal shop at Google with a laser cutter that can cut these in bulk. If you happen to work for a company that doesn't have a laser cutter shop, not a big deal. You can find plenty of places on the internet where you can upload your CAD files. They'll cut them and send them back to you. If you've never worked with a laser cutter before, though, I recommend you try one out first before you send it off and commit to a bulk order and get a feel for what works and doesn't work in this kind of design. But again, the moral for this part of the story is that you can build an enclosure too, and laser cutters are cool, so you should try one out. One more thing before we move on, though. I mentioned we wanted to build a lot of these. We built 75 in the first batch to spread around Google, and we thought that was going to be more than enough. But they were so popular that we built another 75, and even that, frankly, we could have used a bit more. So once you have this many devices, and honestly, once you have more than, say, 1 or 2, you want a way to disambiguate them, to tell which one's which, because at some point, someone will have a problem. They'll say, hey, man, can you look at this device? And you'll say, sure, I'm busy right now. Drop it off at my desk. And maybe they'll put it next to one that looks just like it while you're away. And then you end up looking at the scorch marks on the case to figure out which is which. So think ahead. Give each device a serial number. Keep track of it in a spreadsheet somewhere so you know how much inventory you have left to give out, or who's got what, or maybe what the history of individual devices are.
So we now have the hardware prototype to hold over our application developers for a short term. In parallel, we were working on finalizing the SOM for smart displays. We evaluated certain options in our roadmaps and kickstarted another series of discussions, only this time it was with the SoC vendors. We eventually selected a Qualcomm SOM called as the STA624 for the Lenovo, LG, and JBL devices that are launching this year. Powering this is an 8-core A53 with an Adreno 506 GPU that supports display and camera. It's plenty capable of driving a smart display, and of course, a bunch of other potential devices that you may want to build as well. On the STA624, Google will offer free stability fixes and security patches for 3 years with options for extended support. To give you a more concrete idea of the hardware we are talking about here, here's a photo of the top of the SOM. You can see the SoC, the Wi-Fi, Bluetooth module, the memory, all mounted on a discrete board. Here's the underside of the SOM. The main thing going on here are those 3 high-density connectors with 100 pins each. These pins make up the SOM's interface to the outside world. Here's a little deeper dive into the SOM's pin-out interface. The pins carry power, GPIO lines, and a wide variety of peripheral buses in and out of the SOM. Wow, looks a little overwhelming, doesn't it? However, you wouldn't need to worry about designing this if you were using Android Things to build your devices. Pin assignment has been standardized along with the rest of the SOM so that the underlying platform knows what the expectations are. In some cases, you'll also have the option of laying out the SOM circuit flat onto your board exactly as specified, according to this interface. However, it's much faster and easier to just build a carrier board that the SOM module can plug into.
So if you get one of our development SOMs, it'll come with a carrier board that has some common I/O pins broken out onto standard size header so that you don't need to deal with any of these high-density connectors. But when you build a device for real, for mass production, you'll likely want to spin your own carrier board that connects to whatever hardware you need for your device. For smart displays, we came up with a reference carrier board that we asked our OEMs to follow. You can see in the slide here that in the middle we have the SOM, which again is the CPU, the Wi-Fi, and other important parts, and the peripherals are connected around the outside. We standardized on button and sensor connections in this reference design, specifying which GPIOs they should connect into, for example, to simplify our work on the software side. Because we're working with 3 OEMs simultaneously, we wanted to avoid as much as we could unnecessary customizations across OEMs. So everybody, for example, plugged their volume up into the same GPIO on the SOM. One other thing we specified in the reference design here is that the microphone mute circuit should be external to the SOM and implemented in hardware, so that when you mute these devices, the mics are electrically, physically disconnected from the SOM, so that even in the face of some sort of successful software exploit in the future, there's no way to unmute the device in software. Similarly, we specified as part of the reference design that the camera mute should physically cover the lens of the camera so that there's no way to unmute the camera, so to speak, in software. We did leave some room for OEM customization. For example, they could select their own microphones. They could build their own audio output stages. And they had some leeway on display choice as well. This is the next revision of our development kit. This is what came after the wooden kits that I showed earlier. This one is built according to the reference design, and it's using a lot of the production components that we have in real devices. This time around, the entire front assembly was put together by an outside firm, and we didn't have to do any of that. This case happened to be in acrylic. As you can see, it used friction-fit grommets to connect the standoffs to the back. These sometimes came loose if you over-tightened them, but you could fix it with a little bit of super glue if you had to. From the front, what we have here is the exact same touch panel, camera, and microphones used in some of our production devices. We added this acrylic back at Google, which held the speaker in place and really just gave the front something to lean up against so that it was at a similar angle to what we were expecting for the production devices. Inside, these are essentially the Qualcomm SDA624 SOM plugged into a carrier board that matches the reference design. This is actually one of the earlier versions, which we called the FEP1. And in these versions, the amplifier and the display interface were on daughter cards that plugged into the carrier board. But on later revisions, we had it all flattened down onto a single carrier board. We completed these kits in the beginning of December of last year. If you're not aware, CES is January 9th. So we basically had just a month to go before the big show where we were going to show off these devices at CES. So it was a little nerve-wracking, especially in those weeks leading up to the delivery of these devices where the CES was getting closer and closer. But in fact, the application engineers had gotten off to a great start with the wooden devices. And we sorted out the platform bring-up on the Android Things side relatively quickly. So it's really kind of amazing that 1 month before this huge demo at CES, we were able to completely swap out the hardware. We moved the entire development team, platform, and application engineers from those wooden prototypes over to devices running on a completely different SoC without a hitch. And this is because, thanks to Android Things, the smart display application is totally independent of the platform. You can see how this was useful to us because we had this kind of provisional situation where we needed to bring up temporary hardware before the real stuff was ready. but this can be really useful in production devices as well. You may ship this year with a certain profile, a certain piece of hardware that you need, and then next year maybe you want to cost it down, or you may want to add new features and switch to a more powerful piece of hardware. And because of this, you can easily reuse the application software across a wide variety of hardware platforms.
So around the same time as our reference hardware was being completed, our OEM partners Lenovo, JBL, and LG were busy building out their own devices based on the reference design that we showed before. Those arrived at Google even closer to CES. We got them with just about 2 to 3 weeks to spare. But again, the transition was relatively smooth. We hit a few bumps. For example, on one of our devices, the camera looked green, which we eventually traced to a missing capacitor, but essentially nothing that we couldn't sort out on time. CES was a lot of work. I remember cursing whoever it is who schedules it so close to holidays. This is a picture of our war room that we set up a few weeks before CES. We spent a lot of time here planning the demos, adding features, and fixing last-minute bugs on the device and on the backend servers that make it work. On the demos, we planned to show rich integration with other Google services, such as YouTube, Photos, and Maps. This is a picture of a little kid's room that we set up in Mountain View, which had Nest cameras pointing at it, and we could check in on our little Android baby all the way from Vegas. Our hard work and careful planning paid off, and the demos pretty much worked like they were supposed to. We had some issues setting up the venue and a few hardware glitches, but we brought backups expecting that to happen. The reception we got from the press and users at CES was very encouraging. When you're hard at work on something in secret, it's hard to gauge how the outside world is going to react to it. Getting this kind of positive feedback was a great shot of motivation for the team and helped further galvanize the effort. After CES, it was time to get out of the demo mindset and back to the work of shipping. At this point, we were flush with hardware from our OEM partners, and the program was ramping up. Up till now, we were handing out a single software build to all our developers, but now we needed to expand out. Fortunately, Android Things makes this super easy using what we call as channels. Our developer console allows you to manage, release, and update channels over time. You can get a lot more details on how this works in Adam and Amy's talk tomorrow. So for smart displays, we established multiple channels for our internal user segments depending on their needs. For example, our developers have medium to high risk tolerance and can replace components as necessary. We have a dev channel for them. We also have a canary for high risk tolerant developers where we roll out daily builds. Of course, we have a different channel for our QA or testing teams so that we can give them early access to builds that we want tested. At this point, we also have hundreds of Googlers who are testing out smart displays and giving us feedback on features. These people need more stable channels, and they have low risk tolerance. So we roll out stable weekly builds for them with known good functionality, and we skip builds in case there are issues. We are getting close to the end of the talk, but I want to cover one more thing before wrapping up. In this day and age, if you are shipping software, you never really need to be completely done with it. If you are building a website or a mobile application, you can roll out bug fixes whenever you will. But when it comes to hardware, you only get one shot at it. Once it's in the hands of the user, that's it. There are some things that even software cannot fix at that point, so you better get it right. You also just cannot keep the factory running continuously, though, making small tweaks here and there. You need to purchase your building materials in bulk, and since it's still early in the process, you're not going to be ready to buy in mass production quantities. Also, the tooling and testing takes some time to set up and change. So this process usually happens across a few builds that are standard in the hardware development lifecycle. You can read up more about those on internet, but I'll cover it briefly today. So we already talked about the prototype phase. The next phase is the EVT, or the engineering validation test. For this phase, you're trying to validate that you got your schematics right, you don't have any layout issues, and your components work with each other the way they are supposed to. If you're still considering different design options, you can iterate on them. This is a good time to do so. This essentially represents the first attempt at building your boards the way they'll appear inside your final device. The enclosure is typically still not final at this stage, so you may want to keep the boards hot glued, screwed, or taped just to keep them from flipping around. The next stage is the DVT, or the design validation test. The purpose here is to verify your production processes and equipment to ensure that they are meeting your final specifications. The devices we got for CES were what we called as pre-DVT. They were soft-tooled, which means that the molds used to cast the plastics were made of a soft material like silicone. Again, you may want to do a few builds here until you get to a point where you know that there are no fixes that would need a hardware respin. You ramp up quantities as you get more confidence, and eventually you want to get to a run with hard-tooled plastics. The PVT, or the production validation test, is typically the last build that transitions into mass production. Hopefully, by now, you've logged in the final software that you will be flashing in on these devices. At this point, you're also hoping that your factory is pretty much running on autopilot without any manual intervention. Finally, your product is ready to go to mass production, which means it's ready to be on shelf. At this stage, you're ramping up production and focusing on making process improvements to improve the yield. You obviously want to continue testing it for the next few months, though, as well as establish some sort of reliability testing. So that's how we build smart displays from prototype to production. To reiterate, having Android Things as the underlying platform helped us in every step of the way. First, thanks to the Android framework, our software developers could focus on building application features without having to worry about the underlying platform. Our system on module, or SOM solutions, allowed them to swap out underlying hardware seamlessly as we moved from one prototype kit to the other without affecting the app layer. And yes, while we needed it to do a lot of work to bring up the SOMs for smart displays, you don't need to do any of this. The Smart Display SOM will be ready for your use soon. Our update and device management features allowed for fast iterations and easy maintenance of multiple devices on the field. And finally, our security features mean that our OEM partners and users don't have to worry about the security of these devices.
So we have a lot more to show you at I/O. Come and see us at the Android Things Sandbox Dome, which you can see on the left side of the map here. The entire dome is filled with Android Things demos, and it's open after hours as well. You can see how we leverage machine learning, Firebase, and the cloud platform. And you can also have an up-close look at the prototypes and the devices that we talked about here today. By the way, you'll notice Android Things-powered devices outside of the Sandbox Dome as well. There's survey boxes all around I/O that are built on top of Android Things, and a large human-sized robot roaming around ready to take a selfie with you. So you can come to our code labs as well, shown sort of in the middle area of this map. We have code labs showing how to work with TensorFlow, how to work with Cloud IoT, and how we made the survey boxes that are around I/O, and even more. There are 7 more sessions on Android Things coming up today and tomorrow that go even deeper into some of these topics. Finally, have some fun at I/O. We have a scavenger hunt going on, shown at the link here, g.co/IO search. I won't give away too much, but you'll run into some machine learning enhanced flowers, which are pretty cool. And if you solve all the puzzles and make it to the end, then you'll get a piece of developer hardware to take home for yourself. With that, I'd like to invite you to go build some hardware. And I hope that we're leaving you with some new confidence that you too can build a device with Android Things. Go to the link mentioned here to get started today. Thank you.